Okay guys, currently out here being blinded while y'all do the quiz. Just wanted to record this video for you guys real quickly so that you can look at this tonight for your assignment. So again, I told you guys that we hadn't talked about gravity yet. So we do need to finally talk about gravity because there is an acceleration due to gravity that speeds us up as we fall. We don't fall at a constant rate. And so free fall, whenever they talk about something falling in free fall, it's in particular experiencing minimal or no air resistance. Very often in this course, we're going to say there's no air resistance because that complicates things a lot. So most of the time we're going to assume, or it's going to say falling with no air resistance. Now we have a little constant here, g, which is the constant acceleration due to gravity on Earth. So on Earth, our acceleration due to gravity is 9.8 meters per second squared. And again, what that means is as something drops, it goes faster and faster. I'm not falling at the same rate, yeah? Now again, if we ignore air resistance, yes, which we will for most parts, or most cases, all objects fall with the same constant acceleration regardless of mass, how heavy they are, the shape of them, or the size. When there's air resistance, we know that yes, things are going to fall at a different rate. But without air resistance, it's the exact same thing. I'm going to show these videos in class to you guys to kind of show that this was scientifically and experimentally verified. So we can use our kinematic equations to calculate velocity and position with objects in free fall. What we do is we replace A, my butt's burning here, with G, or we round actually 9.8 to 10. That makes our lives so much easier just to use 10 meters per second squared. So that's going to be our A in our little tables. Yes, if it goes blah, 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 an object is falling, I go acceleration is 10. Now, as acceleration is a vector, we need to be careful with the sign of acceleration. Again, I kind of gave you guys this hint a couple days ago. Depending on our direction of positive that we choose it. Acceleration could be positive or it could be negative. We have to be careful. Now, I think actually this is the only slide that I wanted you guys to do. Let me double check here. Oh, no, I didn't. Okay. So if I throw a ball down, and I decide to call that direction positive. So I am calling downward positive. I get to choose that, right? Now, gravity always points where? Gravity always points downward as well, right? Always. That's how gravity works. So if I call downward positive, what would gravity be here? Would it be positive or negative? It would be positive as well because it's traveling in a positive direction. Now, if I throw a ball upward and instead I decide to call, whoops, there goes my video. That's okay. I decide to call up positive. So if I call up positive, well, gravity still points downward. So in this case, what would the sign of gravity be? Negative, because I'm going the opposite direction of positive. We get to choose positive, and then I need to make sure my signs align with that. So last little free fall tip here. Oh, I forgot to erase this slide. That's okay. Now, if you're given a question where a projectile is shot up into the air, don't make it difficult. If we throw a ball up into the air and it comes back down, to our hand, assuming that it leaves the same position and returns to the same position, yes, what ends up happening is the time going up and the time, that's t, and the time going downwards are actually the same. It is symmetrical, and we're going to learn this, but again, it's going to follow a parabola on a graph. This would be the time it takes to go up. This would be the time it takes to go down. Yes, it's going to be symmetrical. And we can see that here on the next slide. I'm going to go ahead and keep going, right? This is our position graph. If I use an acceleration of -10, that's my gravity, right? I'm going up, reach the peak, and I come back down. Now, again, as we said here, what do we notice about this graph? What is the line x equals 1 for this graph? Well, here's the line x equals 1. When I'm talking about that line for this graph, what does that line do to my parabola? Cuts it in half, right? So x equals 1 is what we would call a line of symmetry, right? It's symmetrical. And so this is a symmetrical graph. X equals 1 is that line for it. Now it says what is happening to the slope of the graph throughout the time period, right? As my slope goes up, and then I come back down, right? What's happening to my slope? Does it stay constant or is my slope changing? Well, my slope is changing, right? Let's come down here, come on. Slope is changing. And because this is a position versus time graph, what does my slope represent? Velocity. Slope is velocity. So I have a changing velocity, right? That proves to us that we have acceleration because our slope is not constant here. Last little question here. This is kind of review stuff. It says, what is the slope of the graph at t equals 1? Let's see if we can recall this, guys. What is the slope of my graph at t equals 1? Well, right here at t equals 1, I would have a horizontal tangent line. That means my slope is 0 at t equals 1. And that means my velocity, which is my slope, is 0 at t equals 1. What happens when you throw something up in the air is it shoots up, but it starts slowing down, right? We can see this graph start slowing down and becoming flatter. Then it reaches a velocity of 0 in order to change direction. Yes, I have to have a velocity of 0 right there. Otherwise, I can't change direction. So you guys are going to go ahead and copy this note card down. We're going to practice it in class. You can pause the video if you need to copy it, but this is going to be the end of the video. We're going to continue with it in class tomorrow.